The malonic ester synthesis can be used to form substituted carboxylic acids as shown below. The proton NMR for the carboxylic acid product shows 4 peaks. So it looks like it's repeated in there. All right, so for the carboxylic acid product shows 4 peaks, and we're asked to identify the alkyl bromide that was used in this synthesis. So this NMR data is matching this product. And then in figuring out our alkyl bromide, we're trying to identify this R piece of the product. But before we get to that, I want to run through quickly the mechanism and the major concept of the malonic ester synthesis. So when you have this 1,3-dicarbonyl sort of system, the hydrogens that are in between those 2 carbonyls are fairly acidic and can be deprotonated. And so we're using a base here in the first step. And notice that the base is matched to the esters, so that if it were to attack either of those esters and do a transesterification, you'd still end up with the same product. So we're going to draw this base, so OR, whatever it might be, and it is going to remove one of these hydrogens. And so what that's going to do is it's making this into an enolate. And that enolate is going to be the nucleophile that's going to react with this alkyl bromide. So we have that. And in your next step, if you add in the alkyl bromide, this can do the SN2 reaction. So this is going to be an SN2 step. So we're alkylating in between these 2 carbonyls. So whatever that R group was added. And then in this step here, the H3O plus and the heat, we're going to first hydrolyze and then decarboxylate. So we're going to hydrolyze the esters first of all. And so ester hydrolysis we saw in a previous chapter, so I'm not going to draw the mechanism, it's quite long. We're just going to cleave these though and make 2 carboxylic acids. And then when you heat this up, you're going to lose CO2. So we've shown this decarboxylation mechanism a couple of times. So what I'm going to do now is to show you kind of the shortcut for this. So when you decarboxylate, you end up basically cutting this piece of the molecule off. So you can kind of just erase that and notice that it's the same as your product, okay? So you end up forming, the hydrogen doesn't go with it. The hydrogen kind of moves over here, as we've seen previously in our mechanisms. But so the end result is we're ending up with that carboxylic acid, so this substituted carboxylic acid and CO2. And so what we've got here now is we've got this data for the carboxylic acid. So this first peak 1 is at around 12, so that should be the carboxylic acid proton. So we have that. So this would be the signal 1, and we know that by the chemical shift. And then the next thing we see is we've got this 5 hydrogen multiplet in the aromatic region. So that lets us know that we have a benzene ring, and 5 hydrogens means it's mono-substituted. Okay, so this tells us that we have benzene. And so benzene is mono-substituted and we still have other signals. That means it can't be directly connected to this carboxylic acid, or else we wouldn't have these signals. So what I notice is that CH2, CH2. So that's what's bridging this carboxylic acid group and the benzene ring. And so let's go ahead and assign things. So your 5 hydrogens are here, so that would be the signal 2. And then these 2, 3 and 4, are in here. So these are 3 and 4, and it's not necessary that we distinguish those. They're very, very similar in terms of their chemical shift. We just know they're both CH2 groups. They're both split into a triplet because they're seeing each other. All right, and then the key to answering this question is we're looking for the alkyl bromide. So we need to know what portion of this came from the alkyl bromide. So if we look at our model that we've drawn up here or down here, these 2 carbons, the carboxylic acid carbon and the carbon next to it, come from your starting material. So this carbon and this carbon came from the starting material, and whatever that R is comes from your alkyl bromide. So if we look at what we have over here, this carbon and this one come from the starting material. So that means that this other piece here must be coming from your alkyl halide. So that means your alkyl halide has to have this benzene ring, the CH2, and then a halogen, which is a bromine in this case. And so this matches A.